Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibration. Last lecture we dealt with the concept of mode shapes. We had an introduction to response to initial conditions, and we continue our discussion later on the dynamics of a body which can have 2 degrees of freedom, but the system as such does not have 2 masses. So, it is still a single mass, but having 2 different degrees of freedom in contrast to what we discussed for a 2 degree of freedom system. So, such dynamics of 2 degree of freedom system will be explored in today's lecture. Okay, so the response to this 2 degree of freedom system to any arbitrary initial conditions has been discussed that it is going to be a contribution from both the modes, and hence we wrote as a general response or a general solution to be A1 cos P1 t minus phi 1, which essentially is accounting for the contribution from the first mode having the natural frequency P1, and also contribution from the second mode. So, we had this cos P2 t minus phi 2, and A1 and B1 are basically going to represent how much of this, the strength of this contribution to the overall response. And so, we also wrote the response of the second mass represented as x2 t to be as you see here. So, here also the contribution from the first and second mode, and so this is a general vibration response to some initial conditions. And how much will P2 contribute, how much will be P1 will contribute, or for that matter how much will be the contribution from the first mode, how much will be from the second mode, will be quantified through the values of A1 and B1. So, when we say that it is going to be contributed from the first mode, the motion of x1 and x2 are that way related. Okay. So, therefore, what we wrote is that A2 amplitude over A1 is given by the first mode shape ratio, right. And if you remember in the previous simpler example, this xr1 was basically equal to 1, or I may write this as plus 1, and xr2, which is the second mode shape, was minus 1 as a specific case where K1 and K3 are K and K2 is 2K and M1 is equal to M2 is equal to M. Of course, these ratios which are representing the amplitude of the second mass relative to the amplitude of the first mass, that value xr1 and xr2 for the second mode will obviously be different for different configurations. That means, depending upon the value of K1, K2, K3, M1 and M2, these ratios would be a value which will be determined by the relative or the values of all the system parameters like the stiffness and mass values. So, this is the ratio at when the system is vibrating at the first natural frequency, and this one is the ratio of the amplitude, okay, when it is vibrating at its second natural frequency. So, this x2 was modified and was written as xr1 mode shape ratio, mode shape or the displacement ratio for the first mode times A1, because you can see that this will give you the value of A2, and then cos P2t, sorry, P1t minus phi 1, and plus you have xr2 B1 cos P2T minus phi 2. Now, and what we discussed, that these two equations basically define the general response of the 2 degree of freedom vibratory system. And then there are four unknowns here. The unknowns are A1, B1. These are the arbitrary constants, or the values of the amplitudes contributed from the first and second mode respectively. And there are phase angles phi 1 and phi 2, which are also unknown. And the way you recall now the single degree of freedom system, where A1 actually was just A, and this amplitude of the response, which we wrote as x of t equal to A cos omega n t minus phi I. A was a function of the system parameters, but it is mainly a function of x naught v naught, okay, apart from the system parameters, which is captured in the natural frequency omega n. Whereas phi also, if you recollect, phi I, we write it as a initial phase lag, was also a function of all these x naught and v naught. If you recall, the amplitude A was square root of x naught square plus v naught by omega n whole square, and phi I was tan inverse of v naught over omega n x naught. So, depending upon how we initially excited the system, the value of the initial phase lag and the amplitude got determined, right. On these similar lines, in this case also, we will have to extract or find out the values of A1, B1, phi 1 and phi 2 by using not only these two displacement response equations, but we will also have to generate two more equations, which are basically the velocity expression, okay. So, you take the derivative of x1t and x2t to find out the expressions for velocity of mass m1 and m2, and then substitute initial conditions, okay. So, when you substitute the initial conditions, you get all the four constants, because now you will have two displacement equation and two velocity equation, four equations and four unknowns, and straightforward mathematical exercise to get the values of the unknown constants A1, B1, A2, B2, A1, B1, phi 1, phi 2. Once these are known, your x1t and x2t will completely get defined, and then you can find out the response at any instant of time. Okay, now we take this example of a forging hammer. We discussed this as an example of a 2 degree of freedom system in the introductory lecture, wherein a hammer or a top drops from certain height suddenly on the workpiece here. So, this is a workpiece, and then when it drops on the workpiece gets forged. So, this is like generating a forged workpieces, and so this is an anvil on which the workpiece is mounted, and this is the total base structure, and then that structure is isolated from a huge concrete bed here. So, this is a bed, and it is again isolated through an isolator here from the ground, okay. And you already know that our objective many times is to ensure that this transmitted force to the ground is as low as possible, so that the forces do not transmit to nearby other sensitive equipment or machines, or even the building structure, so that they do not excite vibrations in the respective structural elements. So, if we want to model this as a vibratory system, one may assume the bed to be huge, okay. So, you will have to figure out how much is the mass of this entire anvil, okay, and how much is the mass of the bed. Based on their relative masses, you may even model this vibratory system as mass of the anvil and its own isolator elements. So, this you can club as one single stiffness element, okay, which isolates the anvil from the bed. So, I can treat this bed to be large enough so that its mass, if its mass is too big as compared to the mass of the anvil, I can simply model this as a simple single degree of freedom system. Okay. But if the bed mass or the mass of this entire concrete bed is not significantly large, okay, a thumb rule could be 10 times large, then I cannot use the bed to be a fixed or a large inertia, then I will have to model this bed also. So, now I am going to add one more mass, and that of the bed, and the bed is itself isolated from the soil or the ground using isolators which are shown here. Now, it becomes a 2 degree of freedom system. Okay. And I will tell you some basic ideas as to when do you really want to model a particular system as a single degree of freedom or a multi degree of freedom system. There are some basic thumb rules which you can follow, but if you want to be very accurate in terms of estimation of natural frequencies and the response, then probably you can make the system as involved and little more comprehensive, while essentially maintaining the size to be manageable. Otherwise, if you make it too complicated, you will take much longer time to calculate and then estimate the response and find out too many natural frequencies which are not necessary or may not be essential. Okay, now having seen the model to be like this, we can again assume this to be x1 and x2, and then we can also write the response as we have discussed earlier, that it will be general response will be a1 cos p1t minus phi 1 plus b1 cos p2t minus phi 2, then x2t will be xr1, sorry, so I will write this as xr1 a1 cos p1t minus phi 1 and plus xr2 b1 cos p1 p2t minus phi 2. Now, here, since there are 4 unknowns, I would like to see what are the initial conditions. The disturbance here is like when the top drops on the workpiece, there is a sudden transfer of energy to the workpiece, and we assume, of course, you can make it little more complex and a little more involved by looking at what is the coefficient of restitution and how the collision is taking place and whether the impact is the collision is inelastic or elastic and so on and so forth. But for a simple case, if I assume that this hammer acts or falls on the workpiece and does not bounce back, then we can say that there is an initial velocity which is imparted to the anvil. Okay. As a simpler case, you can find out depending upon from which height this hammer is dropping, and you can find out what is the velocity of impact on the workpiece. That is very easy to get. So, it actually gives me, so again let me take these as, in this particular case makes sense to consider x1 and x2 positive downwards, and then there will be a velocity v1 which will be at t is equal to 0, which you can find out. Of course, the lower bed is not subjected to any initial displacement nor initial velocity, and the velocity is imparted only to the top mass. Okay. Of course, as time progresses, it will get translated, or the velocity will of mass mb will also be non-zero, but at t is equal to 0, definitely we know that the value of x1 is 0 and v1 is not 0, because that is the initial velocity that the anvil will receive from the impact of the hammer. And so, x2 is also 0 and v2 is also 0. So, our initial conditions based on which I can find out the unknowns is that at time t is equal to 0, I can say x1 is equal to 0, x2 is equal to 0, because before the hammer strikes we assume that the system is stationary, it's not perturbed, it's not moving. And then v1 is going to be a function of the height through which it drops, square root of 2 gh is going to be the velocity. What is the velocity of the bed? That is assumed 0, that it is standing stationary. And using these 4 initial conditions, I have 2 equations in the displacement. I can find out the corresponding velocity. I will just give you an example of how this x1 dot would be like minus a1 p1 sin p1 t minus phi 1 and minus b1 p2 sin p2 t minus phi 2. Likewise, you can get the expression for x2 dot t, and once you get this equation, you substitute these 4 initial conditions and get a1, b1 and phi 1, phi 2. Once you get those, you can substitute them back into these general solution to get an exact solution of the system, which will be valid for this kind of an initial condition. So then your system response is completely defined, and the only unknown there is t, the independent variable. The dependent variables x1 and x2 can be estimated. These are all your responses. Okay, we will take an example based on this in the assignment, but supposing that you get x1t and x2t as your solution, right? That's what you do. You know, again, let me go back to our initial discussion on the vibration analysis. What do? You have a physical system. This is a simplified vibratory model that we have got. This is your simplified vibratory model. Why simplified? Because the actual system could be quite complex if you want to consider all its facets, right? But you try as an initial guess or an estimate, you try based on your own expertise and understanding of the system, you get a simplified few degree of freedom system vibratory model. Okay, and by following your Newtonian approach or energy approach, you generate the equation of motion by using the free body diagrams, which we skipped in this particular case, but we discussed that in the initial part. So then the third step was basically to get the equations, and then the final one or the last but one was to actually solve it and generate the response. Okay, once you generate the response, the last step, which was as a part of the vibration analysis, is to interpret results, right? Just generating a response, if I plot this response to be this as x1t, it's not going to be harmonic, as you all, I mean, I would expect you to know and understand why it's not going to be harmonic, particularly for this initial condition, not for all. But so this will be some response. Similarly, there will be x2t response. What do you make out of this response from the engineering perspective? What, as a designer, what will be the usefulness of this result? And as I said here, the usefulness is probably in the designing of the isolator, a spring or a mount or a isolator here, which is represented simply by a spring, but it will have it can be a spring and a dashpot as a model. Of course, you can include the damping in this whole exercise, but for the sake of basic understanding of a multi-degree of freedom system, we have purposely excluded the damping, but you can always include that. What do you do with these responses in the design of these springs? How do you design a spring? When you design a spring, there is some minimum amount of load that you think of, right? A spring to sustain a given amount of load. Now, many times based on your strength of material or based on your machine element design, you use that spring dimensions based on a certain value of load that it takes or a certain value of spring rate that it has. But that is the reason why this vibration analysis or vibration theory is very important for you to understand. Now you are not talking about only the load. Why? Because you can imagine that both of these masses moving independently, okay, x1 and x2 will have its own motion, right. So this bed is also going to move, and then what will happen is the spring will have, let us say, if I say Ka spring, the spring of the anvil, that Ka is going to be subjected to stretch, which is going to be function of what, x1 as well as x2, and it's going to be function of time t, right. So you may have a case where individually those displacements may be fine for the spring design, but in a particular instant of time the total stretch will be relative, right. If x1 is negative, x2 is positive, or vice versa, the total stretch is going to be much larger than what you might expect. Okay. So when you are designing a spring for such cases, you will have to figure out what is the force for which I should design it, and then the total force could be x1 minus x2 max. That means I will have to figure out what is the maximum extension or a compression that the spring is going to get subjected to, and then based on the stiffness, how much is the force being generated there. In fact, I would also be knowing what is the value of the force transmitted to the ground. Okay, of course that will be based on only the mass of the bed's motion. That means the displacement x2 will finally decide what is the force going in the ground. Okay, so we will have a very nice actual numeric example based on this particular practical case, and we will explore little more than simply the spring design, which will be of interest and practical relevance, right. At this stage, let us move on to another related to degree of freedom system, and now we are going to look at the motion of sort of a car body here, and see what kind of a natural frequency and mode shapes we get in this particular case. So now the system is only one. Okay, so you do not have two masses here. Okay, so the mass is one, but the motions are still categorized as 2 degree of freedom. So if you remember, we said that even if the mass is 1, you can have at most how many degrees of freedom system? 6 in space. Okay, in a planar motion with 3 degree of freedom, you know, it can move this way, it can move horizontally, and it can rotate about an axis perpendicular to the plane of the paper. So keeping horizontal motion to be out of the discussion at this stage, let us focus that this CG of the car body can move vertically, and I define that motion as x. Okay, of course it is a dynamic motion. This is the first degree of freedom, and then nobody stops this car body from pitching. So the pitch motion, which is the angular motion, could be theta t. Okay, it can also have a front, I mean the motion along the horizontal direction, and that motion we are at the moment keeping out of the discussion, just to keep things little simpler. And we will take one more example later in this topic where we will include that degree of freedom as well. Okay, so now this chassis is having, let us say, a CG located here, and as a general case, let me assume that the position of the suspensions from this CG, the rear one is at L1 distance, the front one is at L2 distance. Okay, and now we are supposed to, this itself is a simplified model of a car, isn't it? So this is the first step is already done. What we are now trying to do is to migrate from here to actual solution. Okay, so let us assume that there is this body or a car chassis has a mass of m and mass moment of inertia of, let us say, I. Okay, so this this has an inertia m and mass moment of inertia equal to I about the axis perpendicular to the plane of the paper. What do you do next? What is your next step in this solution process? This is a simplified model. We have identified what degrees of freedom should I be using. The next step to get governing equation of motion is to either go through an energy route or through the Newton's second law, right? So if we go by the second law of law, then I can assume that this motion of the car body takes place, and because both x and theta are possible, I could I can show it this way. This is the CG. Okay, there is a spring over here, and then there is a spring over here. Okay, and then let us say there is an x motion, and then there is, so then there is a rotational motion as well. Right. So this was your initial mean equilibrium position. The car body moves up and then it also tilts. Okay, as a generic motion, both motions are simultaneously taking place. Now, if that happens, we have to look at what are the forces acting on this free body. Okay, so this body will have what kind of restoring forces on it? All right, so there is a spring force here, and we have to figure out what forces are acting on these spring connection points, because that is the connection to the surrounding to the of the free body. Now, what if the displacement and tilt or pitch motion x and theta happens, then sorry, so it will be shifted like this, and then x as well as theta together. So x and theta together would be generating some restoring forces at the spring connection point. Now, how much will be the value of these forces on the free body? Yes, this of course will be so if I call this spring or suspension stiffness to be K1 and this to be K2, so this is your K1 spring stiffness and K2 and so K1, the force which is going to act at this point is going to be for the positive displacement x and positive pitch angular theta motion, what is going to be the restoring force. So it will of course be proportional to the stretch in the spring and proportional, I mean the proportionality constant is K1, right. So how much will be the stretch in the spring in this case? Is it going to be x? Shall I write this as K1 into x? And then of course as you see that the body is moving up and then tilting, and therefore the spring is getting stretched. Okay, so will it be K1 into x? And how much will this be? Of course you can see that the front portion of the body is tilting down, and therefore yeah, so x is going to stretch both of them. but the tilt is going to stretch the left side further, and the right side will try to reduce the amount of stretch because of x. Okay. So, how much will be the force actually? So, based on, if you only look at x, then this force is going to be pulling it down, because the stretch is vertically up, the spring is going to pull it down. This force is also going to pull it down. So, K2 into x is definitely going to pull it down if you assume that the body is being, moving as only the vertical x motion. Both of the two spring positions are going to get stretched, but you see the other motion as well, both x and theta are simultaneously happening. Now, if it tilts like this, then the tilt motion is going to extend the spring position or the spring end further up. Okay, if theta is assumed clockwise positive. So, you can take theta counterclockwise positive as well. It makes more sense that way, but it's okay. Here K1 is K1x is the pulling force because of the stretch, because of x only, but theta is going to add to that stretch, and by how much value will it add to that stretch? So, there will be an additional force here because of the pitch motion, and that is going to be K1 into how much will that be? This is going to be this distance, right? And of course, for small angular motion, sin theta will be theta, and then it will be L1 into theta. Now, that again, reminds us that all these expressions and derivations are all valid for small amplitude. So, even the theta should be small enough. Okay, too large will mean that the assumption of sin theta equal to theta may not be valid. So, for small angles of oscillations, L1 theta times K1 is going to be additional pulling force. It is going to pull it down. So, the total force, if I can write here, will be obviously K1 into x plus L1 theta. Whereas here, as you notice here, that because of the pitch motion causing this front part to go down, whereas the displacement x is going to pull it up. So, the net force, based on this, there would be an upward, because the spring is going to get compressed. If you only consider the pitch motion is going to compress the spring at the front side. So, it is going to be minus K2 into L2 into theta, and therefore, the net force which is going to be acting at the front suspension point is actually, if I replace this as K2 into x minus L2 theta. Okay. So, these are all the restoring forces acting on the free body of the car, and now I will apply Newton's law, where we all know that mass times acceleration, summation of all the forces in the direction of acceleration. Now, x and theta are assumed positive the way you have seen this. So, x and x double dot and theta and theta double dot, they are positive as shown. And so, if I look at the motion along x, or vertical bounce, vertical motion, then it is going to be m x double dot equal to, this force is going to be in the opposite direction. So, minus K1 into x plus L1 theta and minus, because this free body is being subjected to two of these restoring forces. The second one is K2 into x minus L2 theta, and if I rearrange, this is going to be mx double dot plus I can club all the x related terms, and then I have this k1 plus k2 into x, and plus k2, oh wait a minute, yeah, theta related terms, if I take them, then this is going to be k1 L1 minus k2 L2. Okay, into theta equal to 0. All right. So this is one of the two equations we have. We haven't yet looked at the second equation, which is going to be um, m sorry, instead of m, now I'll use I theta double dot equal to all the moments, okay, summation of all the moments acting on the body. So if I use the second one here, I times theta double dot, and I will have to look at all the moments which are trying to restore the motion. Theta double dot is clockwise positive. Here I shall now you may notice that this is the CG position, and the moment, this moment is going to be opposite to the clockwise angular acceleration. So minus k1 into x plus L1 theta. Okay, this is the force which is acting at what distance? How much is the distance here? It is L1, right? So multiplied by L1, that basically is the moment. Okay, so yes, so this is the moment of this force about the CG, for which theta double dot is acting in this direction. Now coming back to the other moment, that is in the same direction as that of the angular acceleration theta double dot. So k2, so this is going to be plus k2 into x minus L2 theta into L2. Okay, so that basically is the equation of motion applying the Newton's second law. Okay, k2 into x minus L2 theta, and that is acting at a distance of L2. Okay, and this one was L1. So now if I rearrange by, again, for the sake of some mathematical simplification, I will write the mass moment of inertia as mass times the square of radius of gyration about this axis. Okay, the axis perpendicular to the plane of the paper. The rg is the radius of gyration. Or maybe it's z axis, I should, and this is the z axis. So if I look at this vehicle as a 3-degree of model, then this is my x, this is my theta, and this is z axis, this is y axis, and it is the theta is about z axis. Okay, theta is about z axis. So about the z axis, the radius of gyration is rg, and so I is being replaced by mrg square theta double dot. Now this will be what? Plus k1 L1 so you can see how you can rearrange the terms here, and so this is going to be minus k2 into L2 into x. So I am clubbing all x related terms, and so then there will be plus k1 L1 square plus k2 L2 square into theta. So I am clubbing all x related terms together and theta related terms together, and that's how the equation number 2 is going to be. So now I rearrange equation 1 here, and then I have x double dot plus k1 plus k2 upon m x plus k1 L1 minus k2 L2 upon m theta equal to 0, which in a simple way I might write this as ax plus b theta equal to 0, where a is k1 plus k2 over m and b is k1 L1 minus k2 L2 upon m. Okay, so it's a simple equation which will help us to understand things better. And then the second equation, it so turns out that it is going to be like theta double dot plus I would write this as b over rg square. You can figure that out yourself, into x plus c by rg square theta equal to 0, where now I will write c to be k1 L1 square plus k2 L2 square over m. Okay, so this becomes my equation number 4, and this one equation number 3. Those are the two final governing equations of motion. So the mass is only one, but I still have two governing equations of motion, two ordinary differential equations to solve for getting the response x and response theta. And general terminology is that this x motion, which is like a vertical movement, is called as a bounce motion or a bounce mode. Okay, whereas the tilt motion about the z axis is called as a pitch mode. Later on, if we bring in all the degrees of freedom, the roll motion is the motion, angular motion about this y axis. So this is basically going to be called, in general, called as roll. This motion about this axis is called as the pitch. The motion, angular motion about the vertical x axis is called as the yaw. The expressions for ABC are all written here, which you can find out numerically based on the parameters of the vibratory system. So if you know the front suspension stiffness, the rear suspension stiffness, and the mass and the mass moment of inertia, or the value of radius of gyration, you can find out ABC, and then these equations are quantified completely. Okay. What is interesting in these two equations is, when you try to find out x from the first equation, theta is coupled with x. Okay, so general motion x or general motion theta is going to be influenced by x as well, or when you have theta, there will be always x happening, or when the x happening, theta will also happen. So if the car vibrates, it is not only going to bounce, but it is also going to pitch simultaneously. the equations are coupled. These are all coupled equations of motion, and we have seen that in a simple 2 degree of freedom system also, that x1 and x2 were not independent. Okay, they were having their own motions coupled to the other one, right. So equation of x1 had the term of x2, and then there was a coupling between the two equations. So in this case, what is the coupling constant which is going to couple the two equations? B, right. So the equations are coupled through B. If B is equal to 0, you can see that the equations become uncoupled, right. The two equations are independent of each other. So if B is somehow 0, equations are uncoupled. Now what is B? B is K1 L1 minus K2 L2 upon M. When we say this B is equal to 0, equations are uncoupled. So for the equations to be uncoupled, what we can say is K1 L1 should be equal to K2 L2. This is the condition for decoupling of the two modes, okay, bounce and pitch. Now when we say they are uncoupled mathematically, what does it reflect into physical motion? So how are these equations turn out when B is equal to 0? It is just going to be x double dot plus ax equal to 0 and theta double dot plus c by rg square theta equal to 0. Aren't they just single degree of freedom system? Okay. So, and they are actually, it's an equation, ordinary differential equation in x and theta separately. So the first equation essentially govern the way bounce motion is going to take place, and when it happens there is no pitch taking place. Okay. In the second equation is representing the motion in the pitch mode, where the whole car body is going to simply pitch without bouncing. Okay. So these are all uncoupled modes of vibration, pure pitch and pure bounce. And what does the physical meaning of this equation? This is the requirement for the two equations to be uncoupled and the two modes to be uncoupled, right. What does that physically mean, this equation? K1 L1 should be equal to K2 L2. Now assume that your CG is located exactly in the center of your span between the two suspensions. Okay. So CG is just symmetrically located between the two springs and K1 is equal to K2. If L1 is equal to L2, that the CG is located in the center between the two suspensions, between the front and the rear wheel. If the two suspensions are identical and the CG is located in the center, then you have two uncoupled modes. Okay, but that's not essential. I can let the CG located anywhere, okay, which can happen if your entire engine is in the front, okay, under the bonnet, and so the CG easily will get shifted towards the front, unless you have heavy weight sitting in the back seat. So if the CG is shifted, then the suspension springs should have the spring rates in a way that this equation gets satisfied. That means K1 L1 should be equal to K2 L2. Even if K1 and K2 are different, your L1 and L2 should be such that you have this equation satisfied. Even in that case, the whole motion is going to be uncoupled, and whenever you disturb the car body vertically, it will continue to bounce if it is vibrating freely, and if you somehow disturb it by giving a tilt motion, it will continue to oscillate without bouncing. Okay. But if B is not equal to 0, then the general motion will be coupled motion. That means when the car body moves down, it just does not move down, but it simultaneously pitches, okay, like this. So pitching and bouncing will happen simultaneously, and that is how the general motion is going to be coupled pitching and bouncing motion. Is that clear? How does that look like? So we have an animation here which will give you a pure bounce, okay, only X happening, no pitch motion. The suspension springs are being stretched and compressed, and the period of this motion is going to be P1. We haven't yet come to that, but we will surely figure out how to get that natural frequency expression. But this is basically the pure bounce mode. In the pitch mode, this is how it is going to rock. Okay, there is no bounce, so the CG is not going to move up and down. It is all going to be pitching about the CG. Okay, so let us go back to what we were discussing here. Now we got the expression like x double dot plus ax plus b into theta equal to 0, and theta double dot plus b by rg square, sorry, x plus c over rg square theta equal to 0, isn't it? Those were the two equations. When there is a pure bounce and a pure pitch motion, they behave like a single degree of freedom system, but we are going to now look at a general coupled pitch and bounce motion. Okay, how do we solve these equations? A and B and C, both and all three are defined already, right? How do we solve these equations? What is our general process of solving these equations? We assume a principal motion, right, normal mode motion, where the motion is such that the entire system vibrates at only one frequency harmonically. Okay, it has to be harmonic motion for a frequency. So what is our assumed solution? Assuming a principal motion, assumed solution is going to be x of t equal to some amplitude cos pt, harmonic motion. And in the 2 degree of freedom system, we have figured out a special condition at which this harmonic motion happens. You know, we figured out that when x2 upon x1 is maintained at a particular value, the entire system comprising of 2 masses will behave in a, or will vibrate at its first natural frequency, and the motion is harmonic. So the second degree of freedom can also have and should also have the same frequency. So I am writing this as theta cos pt. Okay. If you substitute these assumed solution in the governing equation of motion, obviously this becomes minus p square capital X cos pt. So cos pt will be appearing in all the terms, so I can take it out. A capital X plus B capital theta equal to 0. Cos pt cancels out throughout. Okay, x double dot is nothing but minus x p square cos pt. Similarly, I can get this equation as minus p square capital theta plus b over rg square capital X. Mind you, cos theta, cos pt appears in all the terms and it cancels out, and this one is theta equal to 0. This is what you get from the second equation if I substitute the assumed solution. And so therefore, I get from this equation capital X over capital theta equal to what? Minus b over a minus p square. And from the second equation also, x over theta is going to be what? P square minus c upon rg, and this is going to be c over rg square. Oh, sorry, b upon rg square, isn't it? Right? What do you do with these? You have two ratios. The way you got in the previous case, you had x1 upon x2 equal to something, x1 upon x2 equal to something. From the first and second equation, you equated them to get the frequency equation. Okay, that's what you can do by equating these two ratios. You can get the frequency equation, and you can solve the frequency equation to get the expression for natural frequency. So if you do that, that's what you get. Okay. These are the same equations, yes. Okay, if you simplify these two equations, that's what you will get, definitely. And then when you equate these two equations, you get a frequency equation in p square, quadratic in p square, and that's what, by solution of this equation, you will generate the response, the expressions for the two natural frequencies. So this quadratic equation called characteristic equation will give the roots of the system P1 and P2. Obviously, if you use negative sign, you will get the first natural frequency. If you get positive, use positive sign, you get the second natural frequency, the higher of the two. And but you can see that they are all functions of what? A, B and C and mass moment of inertia. A and B themselves and A, B, C themselves are functions of the stiffnesses and mass of the system. So these are all system parameters, and obviously your natural frequency is turning out to be the system parameter dependent. Now instead of square root of k over m, you have little more complicated expressions which is expected. Okay, what is this? This is your mode shape. X over theta is essentially your mode shape, right? The way you got x1 upon x2 to be your mode shape. So x over theta is also a mode shape, right? Now it's going to be hard to imagine the mode shape for this kind of a system where the degrees of freedom, one is translatory, the other one is angular motion. We'll try and figure that out. But these definitely are the way to find out the dynamics of a multi-degree of freedom system. You first frame the governing equations of motion based on the assumed degrees of freedom. In this case, we only assumed x and theta as the two degrees of freedom, and then using those degrees of freedom, you could get by solving, you got these ratios which are defining mode shape, and you got the frequency equation. This is your frequency equation, and by solving this frequency equation, these are the two natural frequencies of the system. Now, what is important is we have not assumed B to be 0, which means that B being non-zero, the two equations define the coupled pitch and bounce motion. Okay, that means whenever there is a bounce, there is going to be a simultaneous associated pitch, and vice versa. Whenever there is a pitch, there will be bounce. And these two natural frequencies P1 and P2 are called coupled pitch and bounce mode natural frequencies. Okay, and so if I animate these coupled pitch and bounce mode, the first mode looks like this, almost pitch. There is a bit of a bounce motion that might happen, okay, and compared to the value of the pitch, the bounce is almost negligible, but there is a slight vertical motion that you can expect in this coupled pitch and bounce mode. Now, just to prove that it is actually a coupled pitch and bounce and the pitch is dominating, we simply fiddle with some numeric values there to show you the actual motion. You can see that compared to a very little, if you can observe, a very little vertical bounce motion is taking place, the numerical values are such that the bounce is very small, and then in comparison to the bounce, you can see that the pitch angle turned in the same period is quite large. But the second one gives you an idea as to what this coupled pitch and bounce mode would look like. So, this is a bounce and also pitch. Okay. So, you can see that the body is pitching, so there is a theta motion, and when it is bouncing, when there is a pitch motion, there is also a bounce motion. This is the motion wherein the motion is predominantly bounce. So, you can see that the angle is much smaller as compared to what the earlier mode was looking like. P x theta 1 representing the first of the two coupled pitch bounce mode natural frequency, and the second one, mode 2, I can write as P x theta second one. Okay. So, x theta represent that it is coupled pitching and bounce mode, and there will be two such, because obviously there are two degrees of freedom. So, there has to be two natural frequencies. When the system was uncoupled, we had still two natural frequencies. One was pure bounce natural frequency, the other one was pure pitch natural frequency. When they get coupled because of an appropriate combination of K1, K2, L1 and L2, then the vibratory motion cannot be completely independent of bounce and pitch. I mean, the motion cannot be pure pitch and pure bounce. In that case, when it does not happen like pure pitch and pure bounce, then the natural vibratory motion will be coupled pitch and bounce. But obviously, it is a 2 degree of freedom system, so two natural frequencies should be there, right. So, here we will have P x theta 1 and P x theta 2 as the two coupled natural frequencies in the bounce and pitch mode. Now, the only thing that separates these two apart from the numeric values is the way it vibrates. Okay. So, what happens is that in one of the two modes, bounce will be predominant, right, while the pitch will also happen. So, both motions will happen. In one of the modes, depending upon the system parameters, one mode will be more dominating, that means there will be more bounce than what you observe pitch, and in the second case there will be more pitch than the bounce that you can observe. But you can find out that mathematically there will be always some amount of bounce motion taking place. That's the only difference here. Okay, and so this basically is the coupled pitch and bounce mode. Okay, and you are also observing here that the time period for the pitch motion and the time period for bounce motion will be exactly identical. That has to be, all of them will complete its cycle at in the same period of time. Okay, so there will be a period of oscillation and the motion is going to be harmonic. You can see that the motion is a harmonic motion. Theta is equal to capital theta cos p1 t, okay, and x is equal to capital X cos p1 t, or whatever, px1 x theta 1 t or so, right. So the motion is still harmonic. The only thing is that both motions are simultaneously happening. So to summarize, we took an example on how to find the response to initial conditions, and we took one practical example there, and then explored the coupled pitch and bounce motion of a 2 degree of freedom system, and understood how the natural frequencies of such a system can be found, quite on the similar lines to what we discussed for a typical simple 2 degree of freedom system in the initial part of the lecture. These are a couple of questions on the contents of this lecture. You can attempt them and verify your answers.